Hi, this is Roger from Kanka Labs today with a repair video of a new item I got from eBay as non-functional, a total harmonic distortion meter from the ELV series from the early 80s, and for that time it had quite outstanding specs. It had an inbuilt 1 kHz reference oscillator with 0.005% distortion only, built with a Wien-bridge oscillator, and then the input you could change the amplification between -6 and +20 dBs. You could tune the filter frequency of the output and of the input for a few percent. You even had an output for your oscilloscope, and the resolution was 0.01%, which was unheard of for that time and for that price. But it was sold as broken because you can download the complete schematics and description beforehand. I knew that except for one very interesting component, and that is this one in the metal can, all the other parts are standard components, so it should be, whatever is broken here should be easily repairable. And this thing here, this is a thermal RMS converter. I didn't find any data sheet for that, so this must either have been custom built for ELV, or it is a rebranded type which is sold under a totally different name. So it makes no sense to give you the ELV designation because you don't find anything on Google with that. Anyway, let's first of all check what happens when we power this thing on. So, powering on, and nothing happens, no display. But here are two LEDs lighting up. So let's first of all check the voltages of our supply voltages. Let's start with a 5-volt digital, which is for, of course, here's an, as you might suspect, this is an ICL 7107 3.5 digit multimeter IC, which is supplied with 5 volts. And let's see, yeah, 5 volts are there. And then we have here minus 12 volt. So let's check those. Yeah, plus 12 volt is okay. And the minus 12 is also okay. Let's, to be 100% sure, check if there are any oscillations superimposed on the voltages. So 5 volt is clean. Plus 12 volt is also clean. And minus 12 volt is also clean. So power is there. It's not an issue with the supply voltages, but I suspect, and that's the next thing what we will probe, you can see perhaps here the display is on a daughter board, 90 degrees angle to the main board, and ELV made it at that time that the connection between main and daughter board is with solder junctions. So the PCB traces go up to the edge of the PCBs, and then you have to solder them together, and that is the only thing that takes up the mechanical forces. And you can see also this is a little bit wiggly, and it's this kind of connection is notoriously known to be unreliable. And so that will be the next thing we will probe, if the connections going from the main board to the daughter board, if there is a broken solder joint. So it's quite difficult for me just to do the tracing without getting my head into the camera. And so already the first connection is broken. Second one works. Third works. The fourth is broken again. We already have two. That one is working again. We already have two. The solder quality and the build quality of this kit is quite good. And what do I see next here? Look, the ground connection here to the 4mm banana jack has come loose. So another fault. Let's continue with our continuity probing. That works. Well, what's with this one? Another faulty one, so we have to resolder nearly all connections. So I will spare you when I to see when I resolder them. But already 3 broken junctions, and that is quite typical of non-working ELV test equipment from that time. So another one that wasn't working, and there are at least 5 that have come loose. And another test I always make when inspecting circuits is shining a flashlight from below, just to see if there are any unwanted solder joints. I'll already spare that and make that in with some more patience, because it's quite difficult to make this here in front of the camera. But this is a nice little trick, just to see if there are any hairline connections between nearby solder joints, etc. But at first sight I don't see any suspicious, so don't do it this way, make it always from behind. So I will resolder the daughter board and then come back again and see if our digital display is working. By the way, the 2 LEDs also were not working. They are also on the daughter board. So it took me half an hour to reinforce the 90-degree angle junction with some stiff wire, and I also found another faulty soldering here at one of the 7-segment displays. So now let's turn it on again and see. Yeah, we have a display, and apparently all digits are working. So the first thing is repaired. Now let's take a look at, first of all, the frequency, the 1 kHz Wien-Robinson bridge, if we get a clean 1 kHz signal out of it. What I don't like here, they have used 4mm banana plugs or sockets. That's quite unusual for making audio measurements. It would have been better to put in RCA jacks, which are also known here as cinch jacks. So we need a lot of adapters. So let's first take a look at, with the oscilloscope, what our 1 kHz super clean sine wave is saying. So I'm using here the second BNC connector just for a ground connection and change to channel 1, and let's, well, that does not look all too clean. Look at what's going on. No, that is surely not a clean sine wave. It looks like there's a secondary sine superimposed. Look at that. It's oscillating here. Can't get it triggered at the moment. So it's very difficult to trigger, but when I change the time base, you sometimes can see for just a fraction of a second that there is a high frequency signal superimposed. So there must be an oscillation in one of the op amps probably. So let's do a little bit of improvised circuit discussion. So here we have the Wien-Robinson bridge, and you might know that it's quite important for a Wien-Robinson bridge. There are two things. The frequency determining resistors and capacitors have to be as equal as possible. And second is you need an amplitude regulation, and this is done here in quite an interesting way. They are having this thermal RMS to DC converter, and the output of the first op amp, they use an NE5534. That is a well-known op amp used in hi-fi stereo amplifiers with very low distortion. So this is one of the best you can buy, although it is nearly 40 years out. And the output goes first of all to another buffer amp, or not another buffer amp, to a buffer amp. So we will probe the output of the first op amp, and one of the op amps already was looking a little bit damaged, perhaps that is the reason. And then we probe the output of the second op amp, if we perhaps get a clear sine signal here, but no longer here. And then there is a feedback loop. We have a full-wave rectifier here. And then the signal is fed here with another buffer op amp into, so the amplitude is fed into the RMS to DC converter, and this in the end gives a feedback to keep the amplitude stable, and this is absolutely mandatory. I've already seen circuits where in earlier times they were using incandescent light bulbs which have the right characteristic to stabilize the amplitude. So anyway, the oscillation itself seems to be okay. So let's first of all probe the outputs of the two op amps, the NE5534 at pin 6 of each of them. So I've tilted the PCB a little bit so that you can see it a little bit better. Probably not everything is in focus. I've set the focus to the, oops, to give a sharp view of the oscilloscope screen. So let's first of all probe the output of the main amplifier for the oscillation, and that looks like a clean, really clean sine wave, as it should be, with 200, no, what is it? 500, with 500 millivolts peak amplitude. And that was the op amp that looked a little bit damaged. And now let's go to the buffer op amp, and that is, the amplitude is okay. It's nominal 1 volts peak or 2 volts peak, but this op amp introduces the superimposed oscillation, and let's see if the input of the op-amp, pin 3, there is still the clean signal, so that either the op-amp is broken or there is something wrong with the feedback loop, or the NE5534 op-amps, they must be compensated with usually a 100 picofarad capacitor. You can see them perhaps here and here. And if this compensation, if there's something wrong with it, a bad solder joint or anything like that, then it starts to oscillate, and so either it's broken or it's perhaps the compensation capacitor with either broken or a bad solder joint. So let's first of all just exchange the op-amp with another one that is here on the analyzing circuitry and see if it gets any better. So I've exchanged the op-amp, and and it's gone away. So the output buffer op-amp was broken. Perhaps because it goes directly to the output, it was shorted at one time, or there was a voltage applied in accidentally. So now we have a clear sine signal. We will later analyze the true distortion of the ultra clean sine signal with simply with the audio inputs of a PC, of the sound card of a PC, and see if it gives the stated 0.005 distortion or less. Anyway, the first thing is already solved. So now we can already do a little adjustment. There's one adjustment trimmer. I think it's for the output amplitude, and we'll make that adjustment just in a minute. So this trimmer is for adjusting the absolute output amplitude. We should set it, I've connected it to my trustworthy X-Tech multimeter because it's more exact than measuring with the oscilloscope. And we try to set it to 0.707 volts RMS. The wrong size of the screwdriver. So it's already quite near. It doesn't have to be that exact. So a 10-turn trim put would have been better. So we're nearly there. But even the slightest touch, so that should be enough within 1%. That's even more than enough. So first, our reference oscillator, we shall leave that for later. And now let's check the analyzing circuitry. Before that, we will in short discuss how they are doing that with the circuit diagram. So let's improvise a little bit. I'm just holding the printout of the circuit diagram just with my hand in front of the camera. Basically, the circuit consists of two parts. This one here is a full-wave bridge precision rectifier, which means this one calculates the mean value of any AC voltage that is at its input. And this is averaged out, and then it goes to the input of the analog to digital converter, the well-known ICL7107. But there's one problem which they didn't take into account. the definition of the total harmonic distortion is to take the true RMS value of all harmonics. And here it is not the true RMS value, but they only take the mean value. So that is not 100% correct how they're doing it. The difference to the true RMS measurement usually is quite small, especially if you have a dominating harmonic like the third harmonic and all the other harmonics are much less in amplitude. But they basically have taken a true RMS converter in the Wien-Robinson Bridge Oscillator, so they could have taken another one also here. Anyway, this part of the circuit just builds the mean value, the average value of any AC signal that you put here at the input, and this little trimmer is just for compensating the DC offset of the op-amps. But the interesting part is here. The first two op-amps are simply linear amplifiers. The first one is a buffer, and then we have the second one here, which can either attenuate a little bit up to -6 dB, or if you turn the volume pot the other way around, you get up to +20 dB amplification, because you need a reference voltage that is exactly this 0.707 volts to give you 100% amplitude. So that has to be adjusted at some point, and this is done with a volume pot here for either a slight attenuation or amplification. But this all is still linear. And the interesting, now it goes to two, it branches off either this way or the lower way. And that is the switch, which you at the moment you can't see. I will show it you later, where you switch from 100% reference measurement. Again, there is a third linear op-amp just to give you the right amplitude for the signal, to give you the 100% reference value. So you adjust the volume pot with the switch in this position, so that you get first of all a 100% display for the sine wave, and then you put the switch to the upper position, and then the signal is taking this way. And this is the most important part. This is again a Wien-Robinson T-filter, a band stop filter, so the 1 kilohertz sine wave is filtered out, and it must be the filtering must be extremely good, because if you want to measure 0.01%, that means that the sine wave has to be attenuated by at least 80 dBs. And for that, all the resistors and the capacitors here, they must be absolutely equal and be of there is a very low tolerance. For example, here for the capacitor, 0.5%. So they must be hand selected just to give the right value and to give an exactly equal value. But still there remain tolerances, and therefore is this second potentiometer just to trim it to the absolute minimum. And we will later see in practice that we have to turn as well the fine-tuning potentiometer of the oscillator as well as that of the analyzer, just to give a minimum value. And then we have another filter stage, and that is for suppressing any remaining 50 or 60 hertz mains frequencies, because they could be so overwhelming that after filtering out all the the 1 kilohertz sine wave. Of course, we don't want to measure any mains noise. We only want to measure the amplitude of the harmonics, 2 kilohertz and above. And so that way they made a high-pass filter which filters out quite strongly, quite effectively, mains noise at the 50 and 60 hertz region, etc. And they use quite a lot of different op-amps. For the input op-amps, they are using again these cheap but nevertheless high-end and ultra-low distortion NE5534. Then for the lower passway here, which only gives you the 100% value, they are using, well, let me see, MC1458, as well as here in the high-pass filter for mains frequency filtering, and for the Wien-Robinson bandstop filter, they're using a TL081, so a standard op-amp, but it's important for these filters to have high impedance FET inputs. And so they are, from their precision, they are quite cheap, but the precision is sufficient for this 0.01% measurement accuracy. And here on the upper range for the full-wave precision rectifier, they are using again the MC1458. This looks like quite clever designed, with the exception that here this is not a true RMS converter but only an averaging, although full wave precision rectifier, but gives only the average value. So now let's first check here this trip port, and then we simply connect the output of our Wien-Robinson oscillator with the input, so without any amplifier in between, and see what we get as the output. So as you can see, I've shorted the output, the input, and now I have to put this 10-turn trimmer here to give 0 offset. And we're nearly there, so that was too much. It's a little bit a pain in the ass because of the angle. So this is 0, and this has been warming up now for 2 hours, although the case is not around, and the transformer becomes substantially hot. So it's really at the limit of what it can deliver. And the 5 volt is also, so all ICs are getting quite hot. I don't think this is a bad sign. Oh, we have a hot amplifier. So there must be another fault, because, and this is exactly the amplifier in the filter, so there must be something else wrong. So I wonder, in the meantime, I wonder if this thing has ever been working correctly. So at least we have our oscillator working, and there none of the amplifiers gets hot. But the TL081 here is getting very hot. I cannot touch it. So with a little bit of, how do you say, spit or saliva, that's my usual method of checking temperature. So in the meantime, I've inspected the PCB, especially the soldering, to find out where or why one of the op amps got hot. And with the flashlight method, I found 2 solder bridges, and I found some other issues. First of all, you can see there are a lot of 10 microfarad decoupling capacitors, but they are not very near to the op amps, so they are strewn all over, but at the wrong place. And what is missing? Where are the 100 nanofarad bypass capacitors? And so I did 2 or 3 things. First of all, at every op amp I put at the positive and negative supply rail an extra 100 nanofarad capacitor going as short as possibly to ground. Secondly, you see there's no real ground plane. It's a single-sided PCB, and that's another thing. In a precision measurement device, you should have a good ground plane, and the ground is here moving all over. Third is, as I just told you, I've found 2 solder bridges, and now the op amps are not getting hot anymore. And you can see this little extra 100 nanofarad capacitor here. I've inserted this one because there is a large DC offset which does not impair the measurement itself, but it's quite annoying. And I don't know why they didn't put it by themselves in the original circuit. And because over the weekend I took a closer look at the circuit, I will probably make another video about analyzing and improving this circuit, because there are some points where the engineers at ELV, well, they didn't do it the right way, and at one point they even cheated a little bit, but we'll come to that if I find the time in another video. Anyway, now, of course, I also replaced the 2 op amps, or the one that got hot and the other one near it. I also, just to make sure, replaced it. It's a TL081, so a 20-cent op amp. And now let's check, and I've recalibrated the 0 offset, so now you can see it's drifting between 0 and 1 a little bit, so it's depending on how hot the circuit or how long it has warmed up. And now let's check. The next step is we first of all connect the input with the 1 kilohertz output of the Wien-Bridge Oscillator, and here you can see this little potentiometer for amplification. That is, in the end, you will of course get an external signal from your amplifier here, and that could be either higher or lower than the reference voltage. So you have a combined attenuator and amplifier, and the optimum would be to get this as a 100% distortion reference signal, setting this to exactly 100.0, but it doesn't matter if it's 100.456, etc., because this is less than 1% error. So this works also. And now we try to check we have to check if our Wien-Bridge oscillator and the 1 kilohertz filter, if when we now switch to distortion measurement, if we get really to 0, and therefore, first of all, you can see it's not 0, it's 1.79, but this is not due to the distortion. We have to tune the 2 frequencies exactly in sync, exactly to the same frequency, and this is an iterative process. So we first change the center frequency of the filter, try to get them to a minimum value. The reason for this process is because of the tolerances between the frequencies of the two oscillators. So we see the minimum at the moment is 1.65 here. Now we take the center frequency of the Wien-bridge oscillator and tune it down, and you can see it already goes appreciably lower. And now this was the minimum, and now we have to retune the center frequency, and we're nearly there. Now it become to get really to 0.0 or less than 0.01% is quite difficult, because these are not 10 turn. So we're at 0.01, and this shall be enough. So this measurement now, but measuring the reference oscillator itself with a filter, shows us that the reference oscillator is okay. It has obviously less than 0.001%, even though we don't get exactly to 0. And the filter also works okay. Let me see if we get it perhaps really down to 0. So I finally made it to get exactly at 0.00%, and that tells us the reference oscillator has less than, or all the harmonics are less than minus 80 dB, and the filter suppresses the 1 kilohertz first harmonic at least 80 dB. Otherwise we wouldn't get 0.00, because the last significant digit corresponds to minus 80 dB relative to 100%, because 10% would be minus 20, 0.1% is 1% is minus 40 dB, 0.1% is minus 60 dB, 0.01% would be minus 80 dB. So that's a good result. Of course, due to thermal drift, it sometimes comes back the last significant digit. Now, next is we'll input an external signal from our signal generator. First of all, we can thereby check if, when we use the sine wave, we can check if this sine wave is pure enough. And let's connect it. Of course, first we have to make the 100% comparative adjustment again, and we're nearly there. We can take that. If we change to the amplitude, you can see we have 2 volts peak, exactly the output amplitude of the reference oscillator, and we get the same result. And you may wonder, well, why 971 Hertz and why not exactly 1 kilohertz? This is not because here the frequency, the quartz crystal, is totally out of adjustment. It has to do with the components they choose for the Wien-bridge oscillator and the filter. They took it from the E12 series, and you don't get a combination that is closer to 1 kilohertz than this here. So the reason is simply the available components. Of course, you could use a combination of resistors or paralleling 2 or 3 capacitors, but it's hard enough to get the capacitors to 0.5% relative accuracy. And so that's okay. And now let's first of all go to another frequency. If we now change to distortion measurement, we first have to find the right frequency where we get a 0 display, and that is here. So we have, it's enough to get to 1 Hertz accuracy. We wouldn't need to get it any more exact. And now we change from a sine wave to a triangle wave, and there we get 9.4% total harmonic distortion. And we could change to a square wave, but there we are already above 20%, so that's out of range. We could also use an arbitrary function or anything else. For example, if we change the symmetry of the triangle wave to a ramp, ramps really have the worst or the most harmonics and the worst distortion imaginable. You can see if we just change it from symmetric triangle to a 40 to 60% relative ramp, how seriously the distortion goes up, and at 20% we are already above 20%. But if you know your Fourier analysis, you will notice that there is something not 100% correct. That should be a slightly different value here, and that was one of the other things I noticed when analyzing the circuit. Usually you don't have that high distortion factors. You know something is wrong with your circuit if you measure 9% distortion for a sine wave, and at the lower values 0.1% or less, the thing where they have cheated a little bit here is not so important. But anyway, I already mentioned this in the video, and we'll take, if I find the time, we take a really close look at the circuit, how they did it and what they could have made better. But for this time, this shall be enough. Thing is repaired, adjusted, working, and I would be quite happy now with the state of this thingy here. 20 years ago, when I didn't have the knowledge to see what still could be improved, but now I still want to improve this thing and make a few minor changes so that the result is really absolutely reliable and not just a little bit out of what it should be. So that was it for today, for a little repair video and an introduction to this distortion meter with a lot of interesting circuit details, like a Wien-bridge oscillator, a precision rectifier circuit, a Wien-Robinson filter, etc., etc. So quite a clever design with a few minor issues. So that was it for today. Thanks for watching. If you liked it, please give it a big thumbs up. And bye from Roger, bye from Kanka Labs. Until next time.